It's a real privilege to be here today, speaking amongst so many amazing people, to be part of the Talented 12. I remember back in 2016, I was leafing through chemical engineering news and seeing, like that class and see what those people have been doing so far, and even going back to people like Jose Nelson and Alex Narayan that have really transformed the field of organic chemistry and biocatalysis. It's a real privilege to be here today. And I will tell a little bit about some of the things that I'm interested in with machine-guided molecular optimization and how we target problems with computers. I'm in the Department of Chemistry and Chemical Engineering here at Carnegie Mellon. And, let's start with actually where I come from. I come from a small town in the countryside of Rio de Janeiro, the state. And I had the privilege to attend a free public, the oldest university in Brazil, Federal University of Rio de Janeiro, and with a short stint at the University of Lisbon, where I was trying to make some graphene nanoribbons for putting in electrodes. But in 2014, I had this opportunity of going to Tallahassee, Florida, to really learn how to control chemical reactivity. And what I mean by that was to go and do my PhD under the supervision of Professor Igor Alabugin, where I learned about stereoelectronic effects that really opened a new world to me, literally, where I learned how to think about molecules in a whole different way. And, for just a very short 101, stereoelectronic effects are not sterics plus electronics. Stereoelectronic effects are their own idea of how orbitals interact and how they orient themselves in space. And I have to thank also the people that I had the privilege to work through throughout my career, including here a picture of myself with Igor and Trevor Harris, who was one of the people that was really kind to nominate me for this award. But I still thought that Florida was a bit too hot. And I decided then to move to Toronto in Canada to go to the University of Toronto and the Vector Institute for Artificial Intelligence, where I would try to learn a little bit of how machines, or can machines even learn some chemistry, under the supervision of Professor Lons Puruguzik. And I had then joined the Meta Lab January 1st, 2019, where they have still a robot. And the idea was, okay, how can we empower chemistry to have the idea of a more autonomous way of making chemistry, designing and producing catalysts, discovering new reactions. And I learned a lot. I learned a lot about how we can really infuse computer science and machine learning into how we tackle chemistry. And 3 years later, January 1st, 2022, my group opened its doors here at Carnegie Mellon in these two departments of chemistry and chemical engineering. And right now we count with 4 PhD students, 2 from chemical engineering, 2 from chemistry, 3 master students, and a few undergrads and affiliates that have been working with us diligently. And I'm so proud of everything that these folks have done thus far in the group. And our mission really is on this idea of reaction discovery and optimization in the age of digital chemistry. And my group, we have the idea of making automated computational chemistry together with automated chemical synthesis to making the next generation of catalysts, then discovering the next generation of materials, learning how to make the next generation of drugs by merging automated flow synthesis, physical organic chemistry, the fundamentals, as Professor Ferreira told us about earlier today, and catalysis and reaction design with machine learning computer science. That is all really because I'm really worried, as many of us would be, about the projections of climate change that we have here. And just taking a look at this climate action tracker here for the global temperatures, we see that if we were to go with the policies and actions that we are doing now, really we would be at 2.5 Celsius at the best case scenario by the year 2100. Then we really need to do something else about this, right? That's the main question that drives us. But if you are to be a bit cynical about this whole situation and think that, well, we need a different way of motivating people, governments, and markets, I want to tell you a different story here from Barron's that in February 2019, and then in April, this had this very nice article on the 3 technologies that could create the next $1 trillion markets over the next decade. And the first one they mentioned is CRISPR-Cas9. And of course, that was a beautifully awarded Nobel Prize in Chemistry for Emmanuel Charpentier and Jennifer Doudna in 2020. And I really see that there is a common idea here, is like, how can we manipulate matter? Because the other idea is post-digital computing, what quantum computing plays a major role. And you see first in quantum computing, quantum chemistry and quantum computers with this paper from in 2005 in Science by my postdoc advisor, Lars Guzik, but also much more recent from Google, IBM, Microsoft, and many other big players on this field. And finally, where we play a role on the idea of material science. And, the question really comes to us is to think how, this takes place, right? Because if we want to invent the technologies of the future, we have a little problem, which is it takes about 10 years and $10 million to develop a new material. And of course, we need to escape this paradigm and go ahead and accelerate this. But then here's the question. As chemists, I need to ask, how do we make molecules? And for all conversations that we have about amazing computer science and machine learning that has now pervade our daily lives, we really do not talk enough about how we actually control matter and can really make and break chemical bonds. And usually the protagonists in those events are catalysts, which are a massive part of the chemical enterprise, right? So of all industrial processes, 85% of those are catalytic. And out of the catalytic processes, only 3% of them use biocatalysis, with Mark, for example, being a major player in the field. And for something that's closer to my field, 17% are homogeneous catalysis. But we have a conundrum here, which is by 2050, there's a projected increase in demand of the chemical enterprise of 180%. And we must do a total 30% reduction of absolute CO2 emissions in the chemical industry, because our industry is responsible for 25% of the global energy consumption to make chemicals. And the chemical industry accounts for 7% of the global greenhouse gas emissions. So clearly, we have a responsibility to play a role here. So here's what we need, right? We need to develop new catalysts for better industrial processes. That's good. Problem is that if we use the current ideas to make molecules and make methods and make reactions, it takes several months to years, okay? Luckily, I can say that this is there's a hope here, because computational chemistry, machine learning, and automation are helping us accelerate these timelines. And that is something that's really awesome. And then I want to tell you a little bit how we are playing a role in this. Because the reality is that designing catalysts with machine learning really isn't a straight path. If you like science fiction, you may recognize this maze here, but we are in the era of descriptors and data swamps and human experimenters, protein-based robots, as some would say. But we are going towards high-throughput experimentation, lab automation, and the idea of self-driving labs. But finally, ideally, we get to a point where we get autonomous discovery, right? So for that, we really need to change how we think about Well, the chemical sciences that we have been doing for the past 200 years. We need to modernize the design, make, test, analyze cycle, where we go from a person thinking how we go about it, and then we make in a slow process, we test in a slow process and analyze in the conventional lab session, to the self-driving lab idea, where we use machine learning as our optimizers, and we use robots to make and test. Finally, we have an automated data analysis pipeline for these. And the technologies that enable these things in high throughput experimentation and analysis are now much more available and much more mature, so we can do a robust catalyst synthesis approach to these, or we can implement parallel experimentation on these performance evaluations and kinetics. All of this together with reaction digitization, microfluidics with flow chemistry, and so on. And that's where we were going. And I want to show you an example of a problem that we tackle in this together with Merck and collaborators at University of British Columbia and collaborators at University of Utah, where you start from this E-olefin that under standard conditions, and in this case, the conditions are what you think for a Suzuki reaction. Let's not debate if this is a Suzuki or heck or something else at this point. Let's assume it's a Suzuki. And under standard conditions, you can either have stereo retention or stereo inversion, depending only on the difference of the ligand that you use for your metal center. That's quite interesting, but there were two challenges. Number one, our colleagues at Merck had a very hard time optimizing the yields for these reactions, and let alone to get to more stereoselectivity. In fact, these are the challenges that we had, right? How to achieve any stereoselectivity. And we have a few different ways of tackling this. So we have a set of continuous variables, meaning can I go from 0 to 100 Celsius in temperature? How long I can do this? How much of catalyst can I add? And how much of my substrates can I add? But also categorical variables, which are much more complicated to deal with, like which ligands should I use? Which base should I use? And then there's a harder challenge, which is how to enforce stereo retention, which was one of the goals that our collaborators had. Well, we decided to tackle this by using this new approach on the design, taste, make, analyze cycle, using optimizers and machine learning and robotics. And the way we started was by taking data that our collaborators already had performed with their high-throughput experimentation setting. And we passed this through a multi-objective Bayesian optimization framework. These are fancy sounding words for just saying that this is a machine learning model that learns by doing and essentially learns by each point that you get. And within this framework, we had an automated closed loop where our machine learning algorithm would suggest what was supposed to be performed in the robot in experiments performed on 96 well plates. And automatically, the robot would then send to an online HPLC for analysis of each of these steps. And this is what it looks like for these machines performing those experiments. And what was beautiful here is that for machine-guided reaction optimization, we let you catalyst discoveries that were only possible because we're now having this data-rich experimentation machine learning-guided processes. This really blends with our idea in my group of developing an end-to-end framework for the inverse design of catalysts on the Catalyst Discovery platform. But before I go, I want to leave you with a sneak peek of some things that we're doing on the idea here, critical idea that molecular representation is at the core of chemical understanding, right? And I want to tell you about pineapples because ethyl butyrate gives the pineapple smell that in this ester. And we have to remember the molecules are quantum mechanical, three-dimensional objects that wiggle a lot because they have their own energy associated. And for us to be able to actually encapsulate what molecules are for machine learning models, we must take into consideration those stereoelectronic effects that I told you about at the beginning and fuse them with molecular graphs that can then become much better representations. I don't have the time to tell you all the details about this today, but you can certainly check out these preprint that we have in ChemArchive that was led by Daniel Boyko and Thiago Sugar, two undergrads at the time that performed this work in collaboration with Google Brain and LBL. Well, I would like to thank, during my time at Florida State, IBM, NSF, and XC, during my time at University of Toronto, the Bunting fellowships and all collaborators, and now at Carnegie Mellon, our funders and collaborators as well. And also would like to thank C&EN and for this amazing event and everything they have done through the years, and you all for listening. Thank you so much.
Thank you, Gabe. I really appreciate your talk. I have a question. What advice do you have for chemists who want to incorporate machine learning and automation into their work?
Yes. Many of us have been thinking a lot about this. Of course, we have this NSF Center for Computer-Assisted Synthesis that one of the things that we are thinking about is how to bring more of those topics to chemists at large, right? And when it comes to research, I would say that for now, folks should try to collaborate with the folks that have been doing it. But a lot of it is actually out there. You have MOSI, which is an amazing NSF initiative for learning how to program, and they do have some machine learning aspects of well. Even CCAS, we have some, and we'll continue to have much more workshops on the machine learning aspect of things. But when it comes to automation, there is unfortunately a component of it that still means that folks need to have a hands-on approach to it. Yeah. But I'm happy to talk with anyone that would have questions and would like to talk more about it.
All right. Thank you so much, Gabe.